Folks, thank you so much for coming. Isn't it super strange to be at Pathé and go to the content without 20 minutes of trailers before? I'm finding it super strange, you know? You have to be in the room at the right time, and that never happens in Pathé. Folks, my name is Mauricio. For the past year, I work for Adyen, and I work on a team there that is all about helping developers. So we take care of onboarding, we help developers get up to speed, we help them do upskilling, so getting better to tackle the challenges that they have. Before that, I was with TU Delft as an assistant professor in software engineering there. Software testing was one of my research topics. I still have a small appointment there, so I'm the one teaching software testing for the bachelor. This is my last two projects. I'm not sure when the third project will come, because one of those projects give me a lot of work. And I'm originally from Brazil. I'm here for 7 years now, and I'm very happy about our elections this Sunday. Folks, why do I care about software testing? Let me tell you a story. So this was 2005, and I was working for this very small consultancy, maybe 10 to 15 people, and then a very large company, Verifone. You may all know the company because they do those point of sales that you type your password. They hired us to do a project there, and the goal was to create some software to automate gas stations. This sounds really stupid today because all gas stations are automated today, but back then this was not really the case, and that was the project. And because I had some experience before as working for their platform, we assembled a team, and I was the team lead. And we spent, I don't know, maybe almost a year coding this first application. And then the goal of the software was to run in Central America, so our pilots would be there. So we spent 10 months, we had the first version that we could deploy. And the deploy was something hard, right? We had to go to a real gas station, do physical installations there. We had to change how their pumps work and blah, blah, blah. So it wasn't something we could just keep deploying every day. And then we went to the Dominican Republic to see the first pilot running, right? So we did all the physical installations. It was 10 a.m. The software was working. I was there monitoring the software. Everything was looking very good. At 5 p.m., everything was still good. So then we decided to, have some fun and celebrate that the project sort of worked, right? And then I was super happy. My first team, as a team lead, everything worked. And then I went back to my hotel. I was sleeping, and then maybe 5, 6 a.m. or so, the phone rang, and it was the owner of the gas station saying, nothing is working anymore. And our software had this behavior that if something is wrong, don't allow people to refuel their cars. So they would get the pump, the nozzle, they would do like this, and no fuel would go out. And there was no way for the people at the gas station to fix this. We had to go there, really turn off the software, and then put the pumps on manual mode again, so on and so forth. We went there, we fixed the problem. I did some debugging, I found the bug, I don't even remember what it was. We patched, deployed again, and everything was okay. And everything worked very well for this first week, although, you can imagine that the owner of the gas station was super, pissed with us, and he lost all the trust because the software didn't work for a day. We made him lose money. So this was sort of what motivated me not to focus on software testing, but to take it seriously, right? Because I had software testing in my bachelor. I had the theoretical parts of it. I also had the practical part of it. I was using JUnit on my day-to-day work. I could definitely blame the platform, right? We were developing in C for this, 200 megahertz, 2 megabytes of RAM device with no testing framework. Poor development environment, but I just blame myself because we didn't even think of doing automated testing. We would do lots of manual testing, as you can imagine. We even created a simulator for the pump, so we could, simulate the protocol that the pump would talk to us. And then, as a developer, we would just do manual tests. Of course, we never reached the case that the bug reached in production. So this is sort of what motivated me to focus more on software testing. But now, let's say you want to educate yourself a little bit more on the topic. There are clusters of different books that you can read. And maybe the most common cluster are the books written by practitioners that we trust, right? Like Kent Beck, Steve Freeman, Ned Price, so on and so forth. And those books are all about how you can write test code to support your development, right? So how you can go from small test to small test, and then your feature gets improved, your feature gets developed, so on and so forth. best practices when how to write JUnit tests, so on, and so forth. But then, the focus is usually how to use tests to guide development. Those books are not so much about, okay, I just wrote my piece of software, I wrote a bunch of tests. How can I know that I tested enough? It's very little about software testing per se, right? Software testing per se is more about let's find bugs, which is basically what you find when you go towards more academic books. So if you get books written by researchers, I list two of them here. The first one, actually my favorite, from Mauro Pezzè. It's all about techniques you as a developer can apply to inspect your software and look for bugs. The problem of those books is that they are very theoretical, and if you open them, you barely see source code. Very hard to really try to transfer from what you see there to what you do every day. And then there might be maybe a third cluster of books that are sort of more high level. They talk a lot about software quality in general, quality assurance in general, not so much about verification, so to say, which is what we try to do with JUnit. And the funny thing is that I think all of them have interesting perspectives and cool stuff that we can now benefit. And at some point I was trying to mix and match and get the best parts of these books and try them, and they sort of worked for me. And this is what the talk is about, right? What the best parts of all these different clusters of software testing books out there. And as I said, I like to see those different topics in two categories. One is writing tests to support you as a developer to build features, and then testing as a way to more systematically look for bugs. And techniques such as TDD, design for testability, design by contracts, and testing to find bugs, maybe those are the ones people know a bit less. Specification-based testing, boundary testing, structural testing, that are very common terms in academia. The first time I did this presentation and I put this figure in the book, one of the reviewers said, yeah, but this arrow gives you the impression that you should do these ones first, right? So you do TDD, and then you do these ones later. And then I said, yeah, but everyone knows that software is interactive, right? You just pick whatever makes more sense to you. And then I didn't add the arrow. But then I get emails about this, so I added the arrow to the presentation. So please use whatever makes sense and go back and forth. And then, of course, on top of that, as a developer, you have to take pragmatic decisions because the world is complicated. You want to decide if a unit test is better than an end-to-end test for this case. Should I mock this? Should I not mock that? How much should I test? Because my budget is limited. I have different budgets. Maybe I want to test something more than the others. How can I decide that? And the first thing that I want to point out is what the academics book talk about, that is systematic testing. And systematic testing is all about trying to find ways or recipes so that you can explore your code. And hopefully you will not forget a corner case there. I wrote a paper a few years ago together with TU Delft and University of Melbourne. And what we basically did was we were looking how developers write tests. So we gave them a small program, and they had to write tests, and we were there watching them doing it. And one of the findings was no one follows any systematic approach. People just follow their hearts, right? So they look at the program and they said, yeah, I think this is a nice test case. And then they write the test case. And then, well, this looks like a very nice second test case. And then they keep doing like this. The problem of just following your heart, you should follow your heart, by the way. It's always a good thing to do. And in software testing as well, right? Because you know a lot. Right? So your instincts are very good and very important as well, but maybe you also want to be a little bit systematic so that even if you're in a bad day, you don't miss one of the cases. And this is what this thing is all about. And if you look at other areas, for example, if you look at medicine, there are research showing that medical doctors that use checklists before chirurgical operations, they make less mistakes than doctors that just follow their hearts. Right? And that's not because the doctors there are better than the other doctors, or that the doctors that made the mistakes don't know what they are doing, but it's just because things are very complex, right? And you can make mistakes. There's an entire book about this called the Checklist Manifesto. You also see this in other areas of engineering, so if we try to bring to engineering in a way, aerospace engineering, for example, is full of those systematic decision-making techniques for specific situations. So it's not a bad idea to be super systematic. I'm not going to dive into those different techniques and how they work, because otherwise this would become a tutorial, but just know that those things exist, right? And there are ways so that you can look at your program and you can sort of follow a small recipe that will help you not forget a few cases. And you know, this is way more simple than you might think. So let's say you have a loop, right? Something that we know is when you write a loop, it's very common that developers make a mistake when the list that they are going through has just one element, right? It's very common that we think of the list with n elements, but never with one element. So maybe that's a hint for you on a test that you should write. And this is basically what those approaches try to do. Now, do we need to be systematic all the time? Definitely not. Because as you can imagine, to be systematic, you're going to spend more time testing, right? And your budget is limited. Maybe you can spend your time doing something better. And it's not a problem, right? Because if you see how software works and how we program, most of our methods are simple. So that's what I'm trying to show in this picture, right? So most of the methods in your system have very low complexity. Yeah, this is not me saying, this is lots of empirical research as well. And maybe you also have this feeling, right? Most of the methods in your software, they are simple. And those maybe don't need fancy techniques to be tested. But you know, the tail is very long. And you do have lots of parts of your software system that are very complex. And maybe those are the parts that you may want to invest a little bit more in writing better tests. Yeah, so systematic testing, think about it, especially if you are in a complex scenario. If you are a QA by formation, right? So there are lots of people where their focus is QA. Systematic testing or specification-based testing, equivalence partitioning, those are all sorts of keywords that are very common to this population of engineers that I feel like they are also very useful for developers. Maybe another term that is super popular in theoretical software testing that I feel it's super useful is what they call boundary testing. And think of a program and think of all the inputs and possible inputs that your program can give. You have sort of boundaries there, right? Boundaries are basically, you know, when you're giving an input to your program and then you make a small modification in this input, and then your program responds to something completely different. Right? So your program was going this way, and then the input made your program go this way. Those are boundaries. And empirical research shows that boundaries are the perfect place for bugs. So to illustrate this a little bit more, imagine you have this very simple program. You get a random number. If the number is greater than 5, you get bitterballen, otherwise you get apple pie. If n is 4, you eat pie. If n is 5, you eat pie. If n is 6, then you eat bitterballen, right? So this is sort of where the boundary is. And then empirical research, and actually a paper from the 1994, right? So not super new research. This paper strongly argues that this is where you want to test. And pragmatically speaking, you know, as a developer, you have an if statement there, right? Which is usually where your program takes different decisions. And then as a developer, you have to pick a number to make your if true and a number to make your if false. Maybe for this case, you could pick 2 and 20, but maybe it's best to pick 5 and 6 because then your test is really at the boundary. Moving on to the next topic, because then, you know, you did systematic testing and then you also analyze the boundaries. What else can you do? I would say structural testing or code coverage might be something also very useful. The tricky thing with code coverage is that people usually tend to hate it, right? And when you talk to people about code coverage, they give you all sorts of reasons why code coverage is useless. For example, this one, code coverage can be easily tricked, right? So I can write a test without assertions and I get 100% coverage, but this is meaningless. Or, you know, because my boss wants me to have 90% code coverage and this means I have to write tests for my getters and setters and that is useless. Or because 100% coverage, that doesn't mean much, right? I may have 100% coverage and I'm going to invest a lot of money to get there, but this still doesn't mean that I covered all the bugs. Yes, all those things are very true. Those are all things you can face, but that doesn't mean that the metric's useless, right? So maybe we can use it in a nice way. So what is the proposed way when you see structural testing in more theoretical books? Those Structural testing is more about a way for you to improve your test suite rather than a number that you should be chasing for. So imagine that you wrote all your tests and you used your experience, all the techniques we discussed, and now the question is, are you done? You don't know, right? Maybe code coverage can show you, oh, you missed this, and then you go back and you revisit. Why did I miss this? Was it because the requirements was a bit strange? And then maybe you write a test for it, or maybe not. But then this was an explicit decision, and the coverage was there to help you spot things you didn't test before. So see that I didn't even talk about numbers, right? Because the number really doesn't matter if code coverage is part of the development loop and not just some number you calculate in your CI. And this is basically what I explain in the figure here that you can see on the slides later. So code coverage is all about informing you rather than taking the decision for you. But then you might still be asking, come on, give me the truth. If I have higher coverage, does this lead to better software? This is, of course, a question that many researchers tried to tackle. And I'm going to walk through a few papers. So this first one in 1994, we all love 1994, right? Brazil was the world champion for the 4th time, amazing year. And these people very inspired by that Brazilian team, what they did was they got lots of programs. They wrote lots of different test suites. Some test suites achieving, I don't know, 60%, 70%, 80% coverage. And they would just check, this 80% coverage test suite, how many bugs can it find from my production code? And they analyzed this, you know, in those different test suites. And what they observed is as soon as you get to 90% of coverage, odds are that you're catching most of the bugs that are more likely to happen in your program. And that, of course, makes sense, right? Higher coverage means you're touching more production code. You are more likely to hit a bug than if you don't have a test. They also observed that 100% code coverage is not really magical, right? You may reach 100% coverage, but you may still have bugs. Another paper by 2009 also confirming this, that there's a correlation between code coverage and the effectiveness of your test suite. Although this correlation might not be always linear and easier to explain, but there's still some correlation between these two things. And something very interesting about this paper is that they also observed that, you know, imagine you're a developer and then you have to write a test, and then you have two strategies. One is let me just test something random, and the other one is let me write a test for something that isn't covered yet. And then the person doing the second approach, so being guided by the coverage, is more likely to hit a bug faster than the person that is just randomly testing. So code coverage can also guide you. So if you're in an area where you have no tests, maybe coverage can keep guiding you. What is the next test I should write? Then another paper by 2014. Well, there was no World Cup in 2014. The 7-1 was a hoax. And what this paper noticed was coverage is not always related to quality, right? So the quality of the test suite. However, it is very good to identify under-tested parts of your code base, right? And my interpretation for this is, you know, maybe high coverage, 100% coverage may not mean much, but a 0% coverage means a lot. A 10% coverage means a lot, right? It means your test suite is not strong enough to capture possible bugs that you may introduce there. And those are just 3 papers that I decided to show. There are so many more papers all sort of going towards the same direction. So I'm not saying you should define a coverage number, but you should pay attention to it. Maybe it will help you take decisions, but it should not boss you around. There's no internet. That's okay. The point here was I wanted to show that I feel like we don't use code coverage so much because code coverage is not really connected to the development loop, right? So maybe you have your IntelliJ and then you run coverage there, but you know, it's more like a report that shows up in IntelliJ rather than anything else. And we created a small prototype for IntelliJ where basically as a developer, you write a test, you run our plugin, it calculates coverage, you write another test, and then we show you, yeah, now you touched these lines, and now you're missing these other lines. So sort of a way to really help developers use coverage in the development life loop there. Today, we mostly run at CI, which is when it's very late, if you ask me, right? And maybe that's why no one cares so much about that report. You can try this in your IntelliJ, although it doesn't work for the last version of of the two, JetBrains likes to break APIs very often. The tool is called TestNight. TestNight. The night, yeah? With the K, yes. Then maybe another point is, I feel like we spent a lot of time trying to really define what a unit test is and what an end-to-end test is, right? So a unit test is something that tests one class and maybe mock all the rest. If I test two classes together, is this still a unit test or not? It doesn't matter, right? Or the same discussion from the other side. It's an end-to-end test. But oh, if I mock one component of my end-to-end test, is this an end-to-end test or not? It doesn't matter, right? We are way beyond this. That's not the point. So the point is, again, to maximize feedback. And I like that this book by Google, maybe 3 or 4 years old, has a very nice definition of tests. And they don't split things into unit tests and end-to-end tests. They prefer to talk about fast tests and slow tests, right? So you want tests that are super fast to run. So maybe you can run them 1,000,000 times in your local machine. You can run them in your CI virtually at every commit or so. And then you have slow tests, which are, as the name says, slow. And maybe, you cannot run them at every commit or so. You're going to have to run them every 6 hours. So, you know that if you prioritize slow tests, it's going to take you 6 hours to get feedback. And the point is, you want to now, and what I like about this discussion is if we're doing unit testing versus end-to-end tests, then we have the discussion, which one is better, right? And then some people prefer unit tests, some other people prefer end-to-end tests. If you think about this discussion, I guess no one here will prefer a slow test. Right? 100% of the people here will prefer a fast test. So I think that's a much better way of thinking about tests. Just make sure that you write tests that are fast. Of course, they have to give you decent feedback, right? Otherwise, it makes no sense. But the point is push towards fast tests. And this helps us with all those discussions on Twitter, right? It doesn't matter if you like unit tests or end-to-end tests. You should just write fast tests. And if you think of maybe showing some source code here, if you think of very traditional piece of code in enterprise applications or so, you have your service class. Your service class probably depends on stuff. The question is, should I mock or should I not mock? Right? So should I mock the participant repository, which, we all know this is a Spring data interface that will go to the database. Should we mock this offering repository, which is also a database call? It doesn't matter, right? If I can make it fast, I don't have to mock, right? If it's fast, if it's easy, I don't have to mock. Yeah, so for example, in this particular case, Spring is amazing. I hope you all like Spring. It's very easy for you to just, replace your database with an in-memory database or whatever, and then maybe you don't have to mock. You made your test fast. Again, the discussion is, how can you maximize feedback? Maybe another example now. So this class over here talks to a Slack bot, and it talks to the LDAP to a repository database, right? So it talks to a bot and it talks to a repository. What else? And it also talks to the LDAP server. Yeah. So Mattermost bot, it seems very boring to not mock, so I'm going to mock it. Talking to the LDAP server, I'm not sure. I'm pretty sure no one here likes LDAP, so maybe it's easier to mock as well, right? So it's also all about simplifying your life in a way. Let me look at the clock. Cool. Now, another thing is, we want to write tests, right? And lots of them. And this is not going to happen if writing tests is not easy, right? It has to be very easy for the developer to write tests. And of course, usually if you're just testing one class, a unit test, maybe it's very easy to write the test. Mockito helps you a lot and blah, blah, blah. But then things get more complicated. Maybe you want to write, maybe you decide not to mock a few dependencies, and then you have to help developers write this type of tests. Meaning you should invest on testing infrastructure. And I'm going to show more about this. But first, let me tell you 2 stories. So I think it was 2013 or 2014, I went to Mozambique to work with a team there that they were developing an application there that would control all the donations that Mozambique as a country receives and how this money is then used in the country. So a very important software system for the society there. And it was a C# web system beautifully developed, but they were facing problems with tests, right? They wanted to write more tests. It was just very hard. It was a distributed application, so not microservices, but maybe 3, 4, 5 big blocks, and it was very hard for them to write tests. So basically what we did there, we spent time building some small DSL, some small library for their developers, so that they could write tests in a much easier way. And in the same company that I was, we also gave a consultancy to a company that would develop this e-learning platform for school for kids, right? So the place where you as a parent go and you see your son's or daughter's grade and blah, blah, blah. Also C#, by the way, I don't know why, but the same issue. It was very hard for them to write tests, and we sort of did the same job there. So it became something natural for the company I was working for. So most of our consultancies about software testing at some point was about helping people build infrastructure. Now let me show you some code to make it more clear. So at Delft, we have this piece of software for 1.5 years now that is called Andy. And what Andy does is Andy grades students. So I teach software testing. When students go to do my exam, they sit in front of a computer, they write JUnit tests, and I have 500 students, so I cannot grade manually. They submit this, and then Andy, this amazing tool, grades these things for me. How does this work behind the scenes? So the student submits the code, we get the test code of the student, we compile, we run their tests, we calculate coverage, we do some mutation testing. We have some tests written by the teacher to make sure that the student is reaching things that we want. We do some static analysis, for example. I don't want students to mock this class, so we can write this type of rules. And then this produces the final grade. As you can imagine, we wanted to test this. And then when we were looking at this structure, we decided that unit testing would not make a lot of sense. Because if you, let's say, decide to mock the compiler component, well, you don't have bytecode anymore that you cannot run the tests, right? So it would be too fake. Or if you decide to not run JUnit, how would you then do the rest of the pipeline? How would you calculate coverage? So we felt like we wanted to write more, end-to-end tests, so to say. But then the challenge came, right? So we had to run this entire big engine, and we needed to get feedback and be able to do assertions in any part of this process. Did the code compile? If not, what are the compilation errors? And how do we present this to the student? So on and so forth. So in the end of the day, we created this very simple API that allows us to write many tests. So if you look at the first method over there, this run method, this is something that only exists in the test code base. And behind the scenes, this method is really triggering the real engine of the application. So one line triggers my entire application. How do testers give inputs to these tests? So the input is basically two things. So first is the program that the student's testing, right? So the description of the exercise, which is a Java class. And then, which you see in the first parameter there, so player points. And then the submission of the student. So in this one, the name says it all. The student submitted something where some of the tests are actually failing. Yeah. This run method runs the engine, and it builds up this data structure called result, which contains basically everything that has happened in the execution of the pipeline. And that allows people to do assertions like this. Result.getTests succeeded is equals to 4. There are 2 failing tests, and the many points but little lives is failing, right? So this failing test is even a small method there. So we used assert J, which is very easy to extend, and this was a given for the testers there, and that allowed people to write lots of tests. Let me go back one slide because I have a keyword here that I like very much. Intermediate data structures, right? I'm going to talk about design for testability very soon, and I feel a lot of the challenges in testing real-world enterprise applications is that we jump from one data structure to the other very fast. So maybe an intermediate data structure can help you test your software. In this case, this result data structure was not really needed in the program, right? We didn't really need it. In fact, the first version of Andy didn't have this. This started to emerge when we decided, let's write more integration tests now, and it got really hard. So you can introduce intermediate data structures as to facilitate your testing. And as much as I would like to claim that this ideal is mine, this actually appears in the growing object-oriented systems guided by tests. So this is an existing idea in the community that makes a lot of sense to me. And I'm going to talk about design for testability soon, but I just wanted to connect this idea here. So bottom line here is, if you want your developers to write tests, a lot of them, you have to provide them with some nice infrastructure for it. If it's too hard, they will write one test, maybe two tests, right? Have you ever seen a test that only contains one assertion and it's usually assert not null? Right, that happens. And that's not because the developer, sucks. It's just because it's so hard to do the proper assertion that you just do the easy thing. So if it's really hard to write tests, maybe invest on some infrastructure. And by the way, this infrastructure was so easy that later we invited a lot of first-year bachelor students to write tests, and they were able to do this even without any training, right? Because the API speaks for itself. So you get lots of benefits also in terms of onboarding and stuff like that. Jumping to another topic, that is test-driven development, right? And this is another topic that you see people very passionate about, right? Some people say you have to do test-driven development, otherwise you're going to burn in the agile hell. Other people say test-driven development is useless, you should never do this, blah, blah, blah. And you see opinionated people in both sides, right? Does it really matter? Should you do test-driven development or not? Well, I think having this test-first mindset makes a lot of sense, right? So you have to be thinking of tests from the very beginning. So even when you're designing your application, now if you're going to do test-driven development or not, this is up to you. Research. Test-driven development was an exciting thing for researchers for maybe 20 years now. There are lots of papers on the topics. What you mostly see there is qualitatively. So when they talk to developers that just did test-driven development, what they say is TDD is awesome. I love it. But when you really compare people doing TDD with people not really doing TDD, the effects are not so explicit. So in terms of tests written, in terms of coverage, even in terms of design, as many people like to say test-driven design instead of test-driven development, right? Do we really create better design if we're doing test-driven development? Well, in controlled experiments, we don't see this so much. Of course, those papers are far from being perfect. We're still learning how to measure those things. But what you see in more modern papers, more recent papers, is things like this, right? So what matters about TDD is not that you're writing the test before, but more like this fine-grained way of working that TDD makes you do, right? You're always working in small bits. And maybe this is more important than writing your tests first. So if you have this sort of mentality, maybe you can do this later. It's fine, because you have this, this test-first mentality. Yeah. Then, of course, nothing matters if your code isn't testable, right? So the talk is developer testing, right? That was the title of the talk. And by developer testing, I mean the test that is written by the developer. So you're developing a feature, you also want to write tests for it. And if you write untestable code, then it can be really hard to test. And I feel like there are just a few simple rules that you can follow or things that you can think of that will make your life easy. And the first one is just separate infrastructure from the main code, right? Just split these two things apart, and that will make your life much easier. I think nowadays it's a bit better, right? Because I feel like we sort of stick to frameworks like Spring, which sort of force some separation already. But back in the days with JSF or web forms, everything was, or old PHP or old ASP, it was very easy to mingle things together. But if you just split these two things apart, I think you are already benefiting a lot. Because if your data access is in one side and your domain code is in another, you have the opportunity to decide, do I want to mock this or not, right? And that is your decision. If things are really connected together, then you cannot take this decision anymore. You will have to say, go to the database or go to your cache or go to whatever other infrastructure that your code directly depends on. So just separate this. In this figure, this is sort of my take on the hexagonal architecture, which is a famous architecture over there. And for me, it really helps you. If you follow this architecture, it really helps you to write better tests, right? I have a few minutes to explain. Cool. So the whole idea is simple, right? Inside of the hexagon, you just put your domain logic, right? So shopping cart or some logic for some batch job. And then on the other side, you have all your classes that connect to external stuff. Like you go to a web service, or you go to a database, or you go to SMTP. And those things are outside of the hexagon, but you want to connect them, right? Because the thing in the inside needs to use the thing on the outside. But then you just depend on something in between there, which is called ports. And you can just see this as an interface, right? So the cart repository there is just a very elegant interface on that hides the implementation details of your Hibernate data access layer or whatever, right? I'm not going to discuss here if you need the interface or if you can depend directly on the class. That's not the point here. But the point is having this separation is very nice. The other two things is observability and controllability. It has to be really easy for you to do assertions, right? So it has to be really easy for you to observe the behavior of your software so that you can do a proper assertion afterwards. If you're just doing assert not null, because you cannot do other assertions, this means it's not easy to observe the behavior of your software. And you have to improve this. And maybe that's another discussion I see a lot on Twitter. That is, but I don't want to change my production code to facilitate testing. Why not? If it's a simple change that will facilitate your life and let developers write hundreds of tests, just do it. Make your life easy. Don't try to be super the opposite of pragmatic. And controllability. It also has to be really easy for you to control your software, right? You want to make sure that you can put your software on state X in a very easy way so that you can run your test. If it's very hard to control and put your software on the state that you want, maybe you need to invest on some infrastructure so that this becomes easy. Again, if it's hard, developers will not test it. Finally, to finish it up, flaky tests. We should avoid them, right? Flaky tests are those tests that sometimes pass, sometimes fails, right? Without changing the program, right? So those are super unstable tests. And we don't like them because they are noise and they are not signal, right? If they are breaking, you never know if they are breaking because there's a bug. I think my example of flaky tests, I worked for this e-learning platform, not the one that I showed in this slide, another one. And we had this payment feature there. So people would buy our products. Yeah, and we would have lots of tests for this. And then we would reach the sandbox of the payment gateway. But the payment gateway was super unstable. Unfortunately, it wasn't Agile, because if it was Agile, that would work as very nicely. But it wasn't Agile, so the sandbox was very unstable, so our tests were always flaky. And that meant, you know, the tests were red, but we would still push to production. Of course, at some point, there was a bug in our side, and we ignored because the test, we knew the test was flaky, but we ignored it. So that's why you don't want to have too many flaky tests. I think there are lots of reasons for it. I'm not going to dive too much. If you want to read papers that systematically investigate the causes of flaky tests, they do exist. As you can imagine, there are a lot of them focused on, async awaits, concurrency, external dependencies you have very little control on. But I think my point here is you should try your best to get rid of them, but they will still exist, and then you have to monitor for them. And you have to try to fix them. Maybe the problem is in your production code, maybe the problem is in your test code. Maybe you can fix it. You see some companies investing very highly on research on flaky tests, like Facebook and Google. And Facebook has a very interesting approach towards flaky tests. So the test is identified as flaky by the CI. The CI notifies the developers. And if the developer doesn't fix it in a time window, the CI deletes the test. It doesn't even ask the developer again, because the CI said to you, your test is flaky. You didn't fix it. It is causing noise to other developers, so it's best if this test is not there. They delete it. Is this the best approach? No idea, but it's an interesting one, right? So I think you have to decide as a company what to do with your flaky tests, because they will exist. Some companies prefer to move them to another test suite. Well, then careful with the flaky test cemeterium, right? Because they will stay there forever, and then they will never become a test again. So I think my point is we have to monitor for them. Yeah? Facebook and Google are even investing on some AI to detect those things as fast as possible. Google reports some flaky tests being flaky once every 2 months or so. So those tests are very hard to be detected. And maybe one very interesting insight from this paper is that, is it in this paper? Let me see if it's there. Yeah, it is there. So sometimes you have this impression that the test becomes flaky because the software evolves and it becomes more complex and etc. But this paper here shows that a lot of those tests are born flaky. So they are flaky from day one. So it didn't evolve to become flaky. So they are born flaky. But most important of all, please stop writing complex code. Right? In a lot of cases, it's just because things are so intertwined that it's just very, very hard to test, and then flakiness happen. Right? Concurrency is a challenge. A lot of those bugs happen because of concurrency, and there are no real, if you ask me, no real good ways of testing concurrent problems. That maybe AI will help us very soon. But I feel like if you're in this environment where your tests are flaky because of complexity, try to, split this complexity, move this around a little bit so that most of your tests you have more control, and then maybe those tests that you cannot make not flaky, they are just a smaller set. So this is something I've been thinking a lot lately. That was my talk. Folks, thank you so much. This is all in my book. And there's also my newsletter that I'm trying to write. The newsletter is free. The book is not. But there's a discount code here. Thank you so much.